We're starting chapter 16, chemical equilibrium. So in chapter 15, we studied kinetics, and we learned about how fast reactions proceed. So we're going to kind of set that aside. The extent of a reaction is governed by thermodynamics, and that's something that we'll talk about, I think, in chapter 19. The equilibrium constant is what we're talking about today. Yeah, there it is, chapter 19. The equilibrium constant is something that's experimentally determined, and it gives us a measurable quantity to express how far does a reaction proceed. So if we have a large equilibrium constant, that means that the reaction favors products. And if we have a small equilibrium constant, it favors reactants. So here's one of the things I don't think we directly lied to you in Chem 1A, but we kind of omitted. Reactions don't actually go to completion. Pretty much any of them. Unless you wait a long time. And there are reactions that only proceed a teeny tiny bit, but those are still valid chemical reactions. So we're going to, open that can of worms today. We'll start with just an example. I'm not going to test you on hemoglobin, but I think this is interesting, and it's in the book. So our red blood cells contain a protein called hemoglobin, and this is a substance that enables our blood to carry oxygen. So this is an illustration of hemoglobin, so you can see why we don't use the chemical formula. We just call it HB, hemoglobin. So this can react with oxygen and form a complex. There's a double-headed arrow here, and that means that this reaction proceeds in both directions, a chemical equilibrium. Not all equations or reactions can do that, but many can. So it can go in the forward direction and in the reverse direction. The concentrations of these reactants and the product are going to be described by the equilibrium constant. And what happens is that if you change something about the equilibrium, it's going to respond in a way that restores the concentrations to meeting the equilibrium constant. So hemoglobin takes oxygen from your lungs and brings it around your body. So in your lungs, there's a relatively high concentration of oxygen gas. So higher concentration of reactants, this reaction is going to proceed more towards the products. And if you think of it in Le Chatelier's principle, where if you change an equilibrium, it will react in a way to undo that change. In other words, equilibria are like spoiled children. They just resist everything. Kind of like myself, I don't like change unless it's my idea. So you can probably guess how excited I was about COVID and all of that. But here, this is at an equilibrium, the blood comes into the lungs, and now this is higher. And the equilibrium's like, no, we don't like that. We're going to make it lower. And so it will react with the hemoglobin to lower this concentration. Now, will it get back to what it was before? No, but it's going to try. And then this will travel to the muscles where the oxygen concentration is low. And now that newly established equilibrium, reestablished, now finds that this oxygen level is low, and it's like, no, I don't like that either, and so it's going to shift this way to release more oxygen. Yes?
What drives the equilibrium? What makes these proteins or chemicals or whatever want to be
Well, chapter 19 explores the reasons for the magnitude of equilibrium constants. We'll get to it. That's a good question, though.
3 to 5 business days.
A little bit longer, actually.
Oh.
Yeah. So, that's cool, right? So you've got this protein, right? And it comes where there's high oxygen concentration in the lungs. It picks up oxygen, and it's going along in the blood, and now the concentration's decreasing, and so it's releasing oxygen where it's needed. And then it comes around again. Now it's, given up its oxygen, and so it's going to pick up more. And it just repeats and repeats, and we stay alive, which is, it's a good thing. How does an unborn baby get oxygen? Babies have a special kind of hemoglobin called fetal hemoglobin, and it has a larger equilibrium constant. So it's going to load oxygen at a lower concentration. So we have the mother's blood and the baby's blood, and they do not actually mix. They come close to each other. There's just, thin membranes and stuff that separate them from each other, but they don't actually mix. But when the fetus's blood comes near the oxygenated mother's blood, then the fetal hemoglobin will load oxygen, even though it's at a lower concentration than in the mother's lungs, because it's a special kind of hemoglobin. Any questions? So, an example of an equilibrium.